Hey, everybody. Welcome to the NeurIPS pre-show. I'm your host, Harpreet Sahota, hacker in residence at Voxel 51, and I'm with my co-host, Jacob Marks, who is a research scientist at Voxel 51. We're joined by Shraman Pramanik to discuss his paper, SPIQA, a dataset for multimodal question answering on scientific papers, which has been accepted into NeurIPS 2024. So scientific papers are a huge cornerstone for research. They present complex findings and really push the boundaries of our current knowledge and understanding. These papers, however, go beyond words. They use elements like figures and tables and different textual explanations to really communicate the research effectively. However, the current landscape of datasets for training and evaluating AI systems on scientific papers suffers from limitations that hurt the development of truly comprehensive AI systems in this domain, because existing datasets are primarily text-focused, and they often overlook the super important role of figures and tables in scientific communication. These visual elements frequently present essential data, illustrate complex relationships, and provide concise visual summaries of research findings. Without the ability to interpret and reason over figures and tables, AI systems can't fully grasp the nuances and complexities of scientific research. Shraman and his team's work addresses these limitations by introducing SPIQA, a large-scale question-answering dataset that encompasses figures, tables, and text from various computer science research articles. This dataset is designed to assess the ability of an AI system to understand and answer questions based on scientific papers, and goes beyond just text to include those complex figures and tables. It's a dataset that encompasses a wide range of computer science domains, and again, it incorporates a vast collection of figures, tables, and their associated captions, along with the paper's text. And this bridges the gap between textual and visual content. And without further ado, I'd like to go ahead and bring on Shraman to the stage. Shraman, go ahead and take it away. I'm excited to get into your talk.
Thanks, Harpreet, for the great introduction. So I am Shraman Pramanik. I am a fourth-year PhD student with Professor Rama Chelappa at Johns Hopkins University. And today I am going to present my work, SPIQA, SPIQA, which I did during my student researchership tenure at Google Research earlier this year. So as Harpreet says, so this paper focuses on multimodal question answering on scientific papers, specifically focusing on the figures, the tables, and the scientific text from different scientific papers. So before going into more details, when as a reader, we read a scientific paper, there are various questions in our mind which we try to answer while reading the paper. For example, when reading the abstract and the intro, we often ask questions. So how we are solving these problems, or what data sets we are using, or even more complicated questions like what is the limitations of previous approaches, and so on. And while reading the whole paper, we try to answer those questions. So it would be more easy for a reader if there is a system which can tell the reader that which portion of the paper to look at to answer some specific question. And very importantly, some of these questions are very easily answered by figures or tables, and we do not even need to read the whole paper to answer a few questions. And in scientific papers, like in modern days, the authors often include complex figures and which are dense in nature, so that they express a lot of information both in the main figure and in the associated caption. So in this context, we find it very necessary to build a dataset which would focus on the scientific text, but also on the figures and tables, and build questions and answers so that we can train a multimodal AI system on those scientific keywords focusing on figures and tables. So as I said, the input of the system may be all the figures, tables, and the associated captions from the scientific paper, as well as the scientific text. So the input can be multimodal. And then we can ask questions to the system and it can answer. And then we have developed this QA in multiple different input strategies, which I will come more into more details later. But overall, the input is the scientific text along with the figures, tables, and the associated captions, and the output is like text. to answer the question. Now, there are various scientific QA datasets in the literature, but all of them only focus on the main text of the paper, because mining the figures and tables are often difficult. And that's why all the previous dataset, they only focus on the textual content. And then there are these datasets often lack in are not huge size, because articulating questions on scientific papers is a very difficult task, because the human annotator has to understand the scientific paper, which requires domain knowledge and also a lot of time. And that's why this annotation process is very expensive. And that's why the previous datasets are small size. There are some large size datasets, but they are not free-form. They are fill in the gap type or closed child dataset. So we try to adjust this limitation of the existing datasets. And in this table, we have summarized all the existing datasets and their domains, their number of question answers, number of papers, and so on. And our dataset, SPIQA, is first of its kind. It is large scale, and then it covers all different domains of computer science. For example, NLP, computer vision, machine learning, database, networking, and so on. And it also covers question and answer, focusing on the whole full text of the paper as well as the figures and tables from the paper. Now, first we collected almost 26,000 papers from different computer science domains. And here we chose the only computer science domains for this work, because computer science papers are often freely available on archive. So there is less legal issues to collect those papers from archive. And we can also cover the whole range of papers from different conferences, because also the computer science conferences are also open source. So we collected 26,000 papers from almost 19 different CS conferences. And those papers appeared between 2018 to 2023. So obviously, in future, there is a huge scope that we can increase the size of the dataset by collecting more papers. And then we extracted the figures, tables, and associated captions from these papers. So the total number of tables and figures was almost 270,000. Yeah. So, and then this, more interestingly, the figures in these papers are often of broad categories. For example, some figures are schematic diagrams, some are plot and charts, some are result visualization and other different natures. So a system to understand these figures well should also be able to understand different domains of figures, which are very different from natural images, like the images we see regularly. So that's why the ask understanding the scientific figures from these scientific papers are often much more difficult than understanding natural images. And we also as we collected the papers from archive, we collected the text sources, because in archive, the authors usually upload the text source. But for some number of papers, we have sent to extract the original text. And for those, we used a tool called PDF Figures 2.0 to extract the text, tables, and figures from the paper. Now, then the next difficulty is that the scale, because if we just use a human annotator to read the paper and annotate the question and answer, it won't be economically feasible, because again, the annotator has to have the domain knowledge, understanding of the paper, and understanding of the literature, which is not possible by doing the common annotation tools. So here we have used the proficiency of LLMs to understand text to generate questions. So what we have done here, so first we have mapped the figures from a paper to the paragraphs where it is referenced. And then we used a LLM, we inputted the figure, the caption, and the passage where the figure has been referenced, and asked the LLM to generate a question and also the answer, and also the explanation of why it generated that particular answer. And in this way, we can easily scale up the question generation process. And before doing this question generation, we have done like an extensive pilot study to choose between different LLMs. And at last, we have used the Gemini Pro Vision to generate the question and answers. In this slide, like there is a example of generated question and answer, and the input figure and the passage where the figure is referenced. Also, like for a few questions, for a few figures, we could not map the figure, like we could not map the paragraph where the figure was referenced. And for those, we just input the image and the caption and ask the LLM to output the question, answer, and explanation. And now, so a brief statistics of the dataset is that like the questions and answer both have a diverse length, which has a correlation with the difficulty of the questions, because the questions which have like a longer answer is often explanatory in nature and are more harder to answer. And our dataset have many different kind of questions, like how type questions, what type questions, which are often easier, and why type questions, which are explanatory, and those are harder. Like the obvious question would arrive here, that if we are using our LLM to generate the questions, how can we guarantee the quality? And for that, rigorous human filtering is required. And here we have what we have done. Like we have now for this filtering, human expertise is not like very necessary, because in this stage, this filtering is much more easier than annotating the questions. So in this stage, we have shown the human annotator, the input figure, the caption, generated question and answer, and the human has to say if first of all, if the question is related to the figure, and if the question is like correct, both the question and answer is correct in the context of the figure, and then if the figure is enough to answer the question. And if all those criteria are satisfied, then we keep the question, otherwise we discard. And after filtering our validation set, we have seen that almost 90% questions are kept. The rest of 10% are filtered out, which kind of show that the quality of the question by LLM. So this slide shows the UI, the user interface we have used for this filtering process. And before like doing all this filtering, we have an extensive set of guidelines which the annotator read, understood, and then went into the filtering. And in our paper, we have all these filtering guidelines like in very detail. Now, if our dataset only have these LLM generated question answers, it would be biased towards the model we use for the QA. So we also augment some amount of manually written QA. And for this, we use two previous datasets called CASA and Casper. So, but these two datasets, as I said, only use the text, the text from the scientific papers, do not use the question answer. So we have filtered from these two datasets, we have filtered the question which required some table and figures to answer, and we have kept like those questions. So like more or less, we have selected a subset of CASA and Casper, where the questions also require the figures and tables to answer. And these two datasets, like these two subsets of CASA and Casper, also serve as two additional evaluation set from in our dataset. So overall, our dataset has two portions. One is LLM generated QA, and other is manually human written QA. But all the questions in our dataset require understanding both the textual content and the figures and tables to answer correctly. So in this slide, again, I am showing an example from the CASA dataset where the particular question requires understanding one image from the paper to answer the question. So this is like some validation statistics, like split statistics from our dataset. And this test A is the set which consists of LLM generated question, and the test B and C consist of human written questions. Now we have defined three different tasks to evaluate baseline systems. The first task is direct question answering with figures and tables. In this setup, we only input the figures tables and the associated caption to the system. We do not input the text, the scientific text, and we ask the model to answer the question. In the second stage, we evaluate the model in a two-step chain of thought way, where we still input only on all the figures and tables from the paper, and we first ask the system that figure out which figure or table is important to answer the question. That is the evidence figure. And then in the second step, we ask the model to answer the question based on the reference or the evidence figure. So we have seen that this two-stage chain of thought question answering can improve the performance of the system. And in the third setup, we also feed the whole paper text along with the figures, text, and the captions, and we ask the system to answer the question. So to simplify the technique, we have not done COT with the full text, but we have limited the COT with only figures and tables. And this slide shows the prompt of COT. As I said, it's a two-step way, where in the first step, the model is asked to select the evidence figure or table, and the second step, the model is asked to answer the question. And this is a qualitative example. So from a paper, we feed all different kind of images. As I said, the images can be of different categories, and then we ask the question to the model, and based on the task type, we ask the model to answer the question. And this is another example. All these papers are quite popular in computer science domain, and all these papers have very complicated images, tables, and the model have to understand those, which is not a very trivial task. And for evaluation, all in these three different task setups, we have used different matrices, but we have built baseline with 6 open source and 6 closed source models. Among the open source model, we use Gemini, GPT, and Claude. And among the closed source model, we use Gemini, GPT, and Claude. And among the open source model, we use InstaBreed, Lava, XNMM, InterLM, CogCLM, and so on. And we also tune 2 open source model, InstaBreed and Lava, on our training set. And we see huge improvement in performance, which kind of show that we can build dedicated LLM-based systems for this scientific domain. And we have used 6 different matrices, among which 5 are existing: Rho, Meteor, Rube, Cider, and Bar score. But these matrices are not good enough for evaluating free-form question answering. And for that, we have proposed a new metric called L3 score, or LLM log score, which use the confidence of a LLM as a judge to evaluate the quality of the answer. So how this entry score is measured is also kind of simple. We feed a ground truth answer and the candidate answer to a LLM. Specifically, we have used GPT-4o for most of the experiments, and then we see the logit values. We ask the model to answer in a single word, yes or no. Then we see the confidence score of yes and confidence of no. And from there, we calculate the LLM score as the softmax of the logit value of yes. So if the candidate answer is very close to the ground truth answer, then the logit value of yes would be very high, very close to 1. Then the L3 score will be very close to 1, and otherwise. So going to the main set of results, we have done extensive experiments on all 3 different evaluation sets of our dataset. So in this table, we are showing the results for direct question answering. And among the closed source model, we have seen GPT-4o performing mostly better than other models in majority of the matrices. And in the open source models, all the open source models are kind of bad, and no model is showing consistently good performance. Their performance is more or less in the same range, but it's much lower than GPT or Gemini model. But very interestingly, when we fine tune Instruct, Blip, and Lava, their performance improve a lot, and their performance kind of touch the performance of the closed source models. And this kind of show that we can build very strong, dedicated AI system for this kind of scientific QA task, even if our fine tuning is not huge in scale. Then the previous results I have shown is for direct QA. Then when we include the COT setup, like the two-stage evaluation setup, or the evaluation with the full paper, we see some improvement in performance, like mostly in 2 to 3 point improvement across all models and all different evaluation split. So this kind of show that both the COT's two-stage evaluation setup and the text from the paper kind of help in answering the question. But when we include the full paper, the input becomes huge. So the models which have long context understanding only handle those long inputs. So there is a downside as well. And also this is kind of intuitive, but when we include the captions with the figures, then the performance improve. And because captions often summarize the figure like in a very good way, so figures plus captions is often much more beneficial than only figure. Lastly, we have tried to understand the performance for different kinds of figures. As I said, like figures can be schematic diagram, can be plots and charts, can be scientific visualization and others. And we have seen that some models are very good in some specific kind of figures, but struggle to understand other kind of figures. So for example, this GPT-4o shows a very strong performance on schematic diagrams, but show like low performance on plots and charts and visual. So by this, like we can delve into more detail, like which model is good in which kind of figures and try to improve based on that. So as this is a dataset paper, we kind of deal the first stepping stone on this analysis of scientific diagrams and scientific tables, but there is much more to do in future. And then this is some visualization, like this is a plot, and the question is asking like which method has the best performance on some setup, and the model have to answer the question. And here we also see like our proposed M3 score is often much more effective than the existing like matrices, because existing matrices are often token level, does not try to understand the semantic meaning of the candidate answer. So this is another example, and this time the figure is a schematic diagram. So in our paper, we show much more examples, like its figures can vary a lot, and the questions are often of different kind. Lastly, we have seen that when increasing the resolution of the input image, we can improve the performance, and that's also quite intuitive. And in most of our experiments, we have used GPT-4o for calculating the LLM log score, M3 score. But if we use other LLMs like Gemini Pro or even lower sized LLM like GPT 3.5 Turbo, we can also get similar range of L3 score. But the range of scores when we use different LLMs are often different. So we encourage future users to stick with one single LLM for all the experiments when using L3 score. So recently GPT-4 mini is much less expensive than GPT-4o. So we are pretty sure that L3 score will also work with GPT-4 mini, but the user should stick to one single LLM for all their experiments. So that's the overall high-level description of the work. And to summarize, we have proposed a large-scale free-form QA dataset for scientific papers. We not only focus on the scientific text, but also focus on the figures, tables, and the captions. We have proposed 3 different but well-defined tasks: direct and COT QA with only figure and table, and also including the scientific text. And we have proposed a novel metric for open-ended question answering called L3 score, which uses the confidence score of the LLM to evaluate the quality of the answers. And lastly, we have done extensive experiments using 12 different multimodal LLMs on our dataset. And we also fine-tune 2 open source models to see performance improvement after fine-tuning. So this is the whole picture, and thank you so much for inviting me for this presentation. Our dataset and our evaluation code is is open source, so please feel free to check it out. Thank you.
Awesome. Thank you so much for the overview of the paper. And I'll go ahead and turn it over to Jacob to see if Jacob has any questions.
Yeah, awesome work. This is very cool and definitely represents a significant step up in the evaluation and the ability to train models and take a free form information that is in scientific papers. I had a few questions, one of which you touched upon at the very end when you mentioned that it actually depended and you were able to get better performance when you use different image resolutions, which I could imagine that if you pass in these very fine-grained images that have a lot of different lines with dashes and dots and different symbols on them, and you try to truncate that to 224 by 224 pixels to feed into as patches to whatever model, you're going to get lower performance. But I would also imagine that the prompting that you use in the text side of things would matter. So for instance, you used the prompt template of your professor come up with a question, and then you had a template that you used when you were assigning the L3 score at the end, and you were like, you say yes or no. So I would imagine that the type of prompt template you use there would impact the results you get, and also how much the model stays within that yes/no framework versus potentially veering away from that. Did you do any analysis and ablations around the prompts themselves?
Yes, that's a very good question. First of all, for M3 score calculation, this particular model does not need to be multimodal because it only input, we only input the question, the ground truth answer, and the candidate answer. So we can use any text LLM for this. And we have seen the LLM to be very good at following instruction. So we have not, if we specifically say the model that answer in one word, yes or no, then often the answers would be only one word, but instead of yes, it can say yeah or synonyms. But we often see that model kind of follows the instruction to say in one word. And in certain case, if in the H case, if the model does not is failed to answer in one word, we usually we usually give a 0 score to the model. But I think that's a very edge case, and our code kind of handles those states. But that's as per my experience, that's not a concerning thing.
Gotcha. And then one more big question is a lot of these types of benchmarks will often have a baseline for human performance. Did you do any testing of how humans perform on these types of projects?
Yes. Our paper has a human performance baseline as well. But in our data set, because the papers come from various different domains, even in computer science, it comes from various different domains. Even the annotator who sit and write the answer is not always correct, because the annotator has to have those kind of expertise, which is not possible. So we have done human evaluation on a subset of the whole evaluation set. We have seen the performance of human evaluation is kind of higher than the models, but we are sure that this human evaluation performance is not exclusive, because the human is not perfect in those cases, because they don't have all this expertise. And we plan that in future we would gather different annotators from different and give them the questions where they are expert in. But this is our a plan. We have not done that yet. But more or less, to give a base, we have reported human evaluation in the paper.
Great, thank you.
Thanks again for presenting the paper. My question I have here, a couple queued up about mostly kind of data curation, things like that. But you talked about in the paper the use of both automatic question generation and then this manual kind of curation in creating this data set. Could you elaborate on the balance between the two approaches? What do you think were the biggest challenges in each process, and how did you mitigate any potential biases?
The best case would be write all the questions by human, but that's not scalable. And this is again related to the expertise of the annotator, because the annotators, in that case, the annotator have to understand the whole paper, which is not feasible in large scale. So that's why we have chose to go with the automatic annotation process, and we have done also some experiment that we mix like this automatically generated QA and manually generated QA, and ask like a third person like who don't know anything about our work to classify if the question is generated by a LLM or by a human. And we have seen that for 89% of the cases, the human cannot distinguish between LLM generated and human generated question. And this was also asked in our like by one of the reviewer, and this was done by us in the rebuttal process. So that kind of shows that there is minimal bias in the data set. But again, saying that, I cannot guarantee that there won't be any bias, because there can be some bias which is not visible in human eyes, but visible by other models. So this is one stepping stone. So this is our way to curate automatic questions, but we cannot claim that this is the best way. We have tried to make the bias minimal. We have mixed LLM generated questions with automatic manual generated questions in the whole dataset and kept them separate and evaluated the models on all different splits. But that's our limitation of the work.
What do you see as foreseeable challenges to adapt this current data curation and generation pipeline to maybe a different field, like, for example, biology or chemistry? Are there kind of any domain-specific considerations that you might need to address?
Yeah. So in the beginning of the work, we thought we would also include papers from chemistry, physics, and biology. But in those domains, the collecting the papers and using them for training an ML model is more hard than computer science domain, because those papers are usually published in journals which are not open source, and we cannot freely collect those papers. So that's why those domain is more harder to work. But the team, I am not a part of the team in Google Research anymore, but I know that they are right now they are working on on extending this QA process on other domains, and their recent work is also under review in ICLR. So I know that there are works, so they are trying, but those domains are even more harder than working with computer science. And often those domains, the figures specifically are much more complex. And so, I think that would require more work to do the same thing on other domains.
And how do you see the work that you guys did here influencing kind of the development of future models and even evaluation metrics for scientific paper comprehension? Are there any potential downstream applications of, such AI systems in, research, education, or other areas?
Yeah. So this particular kind of work is related to document understanding. So one downstream would be summarization. Not downstream, but very related task, because here in the COT setup, we are also asking the model to figure out which tables and figures are evidence for the question. And we can also do this for the text, where we ask the model which paragraphs are important to answer the question. So that is kind of related to summarization or filtering out which portion of a long document is important for some given query. Yeah, and then the metric we propose, the L3 score, is very related, because it can be applied to any QA. So evaluating MCQs are easier, but evaluating free-form QAs are harder. And these existing matrices like the Blow, Meteor, they just find the token level similarity. But even the answer does not have any matching token with the ground truth, the answer can be completely right. Or even the answer has 90% match with the ground truth, the answer can be completely wrong based on one single word. So that's why we thought that understanding the semantic meaning of the answer, the candidate answer, is necessary, and the L3 score is exactly doing that. So this metric can be applied to many other Q&A, not only for scientific Q&A.
Jacob, any further questions?
No, thanks so much.
Yeah, thanks, Raman. And if you're at NeurIPS this year, if you're at, in Vancouver, come swing by, the Voxel 51 booth. I'd love to come meet you in person and hook you up with some swag. So please do stop by if you can be in town.
I will be in NeurIPS next week, so I will visit. Thank you so
Awesome.
much.
Look forward to meeting you there. Cheers. And once again, thank you.